Alright, welcome to Organic Chemistry. In this lecture, I want to discuss infrared spectroscopy. Infrared spectroscopy is a technique used to discover information about the structure of a molecule using the interaction of that molecule with infrared light. In a previous discussion, I spoke about some fundamentals that underlie all of spectroscopy. Those are that light can be described as a wave. Waves are characterized by either their wavelength or their frequency. Those are inversely related to each other. Light can be described as an energy. The higher the frequency, the shorter the wavelength, the higher the energy. The lower the frequency, the longer the wavelength, the lower the energy. Infrared is a portion of the electromagnetic spectrum. An electromagnetic spectrum is a range of energies of varying, a range of energies that differ in terms of their wavelength. That is lower energy than visible light, just to the left on the spectrum of visible red light. And we also learned in that lecture that there's a conservation of energy, that energy is quantized, and that when energy interacts with molecules, molecules respond. As a result, if I shine infrared light on a molecule, the molecule will start to interact with that, and we can observe this process. Molecules vibrate. When we build a model of some molecule, we have balls and sticks, but that's not really the best of pictures, because instead of sticks, we probably should think of those as balls connected by springs, because those bonds are stretchy. They can be stretched out, they can be compressed, angles can be bent, they can be compressed and expanded, and so molecules at room temperature, for instance, are vibrating in a variety of different ways. Instead of thinking about a molecule as two balls connected by a stick, it would be, a simple diatomic molecule would be best thought of as two balls connected by a spring, so as shown in this picture. Now, in your physics class, when you talk about harmonic motion, you talk about springs and pendulums and waves and these sorts of things, you might describe them in terms of Hooke's law. So here's a simple version of Hooke's law, which says for a two-mass system, when I've got two balls connected by a spring, the frequency of vibration is equal to 1 over 2 pi, that's the constant pi, times the square root of the force constant for the spring times the mass of one ball plus the mass of the other ball divided by the mass of one ball times the mass of the other ball. Okay, I don't really care about the specifics of this equation. Don't worry, we're not going to do math on it. The important thing to realize here is the frequency of the vibration is related to three things. The mass of this weight, the mass of this weight, and the spring that connects them. Force constant is essentially how easy it is to stretch a particular spring. So a slinky, for instance, has a very low force constant. It takes almost no force to distort this spring. But these springs that are part of the suspension of a motorcycle have a very high force constant. It takes a lot of force to compress these things. You couldn't just do this, with your hands. So different springs have different force constants. If I was talking about a molecule, I've got these, say a simple diatomic molecule, well, I've got the masses of the balls and I've got the forces of the springs. Those come down to the elements. So here, for instance, I look at the frequencies of a CH, a CC, and a CO stretch. And they have different energy, or different frequencies, which corresponds to different energies. Well, what differs between these is the masses of the atoms involved. These are the M and M on that previous slide. 12 and 1, or 12 and 12, or 12 and 16, for instance. And changing the values of the masses changes the frequency. These examples, a carbon-carbon single bond, a carbon-carbon double bond, and a carbon-carbon triple bond, also vibrate at different frequencies. But here the masses are identical, right? 12, 12, 12, 12, 12, 12. What differs here is the bond. So the bond is the spring in our picture, and different types of bonds, single, double, triple here, have different force constants. So the vibrations involved in molecules is going to be related to, the frequencies of the vibrations in molecules is going to be related to the masses of the elements involved and the types of bonding involved. Now you can imagine that if we can observe this vibration in a spectrum, we can learn something about the molecule. We can specifically learn what types of bonds we have, whether we have CC bonds or CO bonds, whether we have single bonds or double bonds, for instance. So let's look at some real pictures. In an infrared spectrum, we have along the bottom here frequency, and this is given in wave numbers. 4,000 is very high, a relatively high energy, and it's down to about 4,500, which is low energy. So the left-hand side is higher energy and the right-hand side is lower energy. That's the x-axis. It's frequency of infrared light. And the y-axis here is percent transmittance. Essentially, if I have a sample of my, in this case, my compound is 3-methylpentane. If I shine infrared light through it, at this frequency, the light does not interact with the molecule, and so all of the light goes straight through. That is, my percent transmittance is very high. Almost all of the light goes through. But at this point, my light doesn't go through. Well, why doesn't it go through? Because this energy of light is the right energy of light to interact with the molecule. And therefore, as light hits the molecule starts vibrating, and some of the light energy is transformed into vibrational energy. Therefore, the percent transmittance is very low. Over here, we see pretty much nothing, and then we see a couple more spikes. What does this tell us? If we look at a number of different instances, we'll see that in alkanes, every time we've got alkanes, we tend to have signals in here. Because it turns out that just to the right of 3,000, so slightly smaller numbers than 3,000 wave numbers, that's the energy of an sp3 CH stretch. So anytime we've got sp3 carbons bound to hydrogen, we would expect to see signal in this region. Because if I hit my molecule with the correct energy of light, those CHs will stretch. Notice this is a very simple molecule, and therefore we see a very simple spectrum. We'll see more complex molecules in a couple of slides. So the first thing that we see is that CH stretches can be observed in the IR. And specifically, we're looking at sp3, that is alkane CH stretches. We can also see alkene CH stretches, but it turns out they're at a slightly different energy. An sp2 hybridized carbon bound to hydrogen is a little bit different, has a little bit different force constant than an sp3 hybridized carbon bound to hydrogen, which is certainly understandable because the bond is made up of different orbitals. The sigma bond in an alkene CH is made up of the overlap of an sp2 carbon orbital and a hydrogen s orbital, whereas the sigma bond in an alkane CH stretch involves an sp3 to a CH. Different force constant, different frequency. And the result is that the alkene CHs, there's a hydrogen here and a hydrogen here in cyclohexene, those have a stretch at a slightly different energy than the sp3. So just to the right, these ones have to do with CHs here, 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 and here. But just to the left, this line right here, that's a signal that's representative of an alkene CH. And so that's this hydrogen and this hydrogen. Now we should be careful. Just because we have an alkene doesn't mean we necessarily have sp2 CHs. So for instance, this molecule, tetramethylethylene, also known as 2,3-dimethyl-butene, has an alkene, but it doesn't have any H's on the sp2 hybridized carbons. So for this molecule, we wouldn't see anything here. We would only see things here. These other signals have to do with other things. But for now, we've noticed two particular signals. If we see signals here, those are alkane CHs, and if we see signals here, just to the left of 3000, those are alkene CHs. So for instance, in cyclohexene, we have both CHs on alkenes and on saturated, that is sp3 hybridized positions. Another thing that we can very easily see in the infrared spectrum is triple bonds. When we've got triple bonds, we tend to have a very sharp signal around 2200. For instance, here I see this molecule that's got a carbon-nitrogen stretch, and see this very sharp signal right around, here's 2200 on my x-axis, so it's a little bit, I don't know, 2240 or something like that. So these aren't exactly at 2200, but give or take a little. This very sharp signal is indicative of a triple bond, and really that's the only thing that happens right here. So if I see a line here in the spectrum, I know I've got a triple bond. We should be careful. We don't always see it. Very symmetrical molecules, for certain reasons, we don't this signal is not very strong. But if we do see a signal here, we know that we have a triple bond. Alcohols. If I have a molecule with an OH in it, the OH, the oxygen-hydrogen bond, has a very obvious stretch. Around 3300, maybe 3200, maybe 3400, depending on the molecule, we see a very strong signal. And it's also kind of obvious, it's rounded. When we look at alcohols, it's going to be really easy to see them. Anytime we see an OH, we'll see a very strong signal in this region. Now we should be careful if there's water in our sample, and that sometimes happens if you're purifying something and you don't clean it very well. You might have water in your sample, and so you might get a false signal in that you're actually seeing the OH from water, which also has an OH. But generally speaking, strong signals in this region are indications of alcohol functional groups. Amines, NHs, have signals in similar area, but instead of being that nice rounded signal that we saw in the alcohol, they tend to be spiky. By which I mean, if you look at this picture and you think of the picture on the previous slide had this large rounded signal. Here we got kind of a jagged signal in this region. But amines are pretty obvious in the IR. CO double bonds, ketones, aldehydes, etc. The CO double bond is a very obvious signal in the infrared. If I have a very strong signal around 1700, I know that I've got a CO double bond, because that's pretty much the thing that comes right around this region. Again, it's a little more, a little less, depending on the example. But anytime I see a very strong signal in this region, I know that I've got a CO double bond. So for instance, this is the spectrum for methyl cyclohexanone. You'll notice this molecule has a signal just to the right of 3000, because if you look at the molecule, there's CHs on these sp3 hybridized positions. It does not have any signal just to the left of 3000, because there is an sp2 hybridized carbon here, but there are no hydrogens on the sp2 hybridized carbons. It also doesn't have a strong signal in this 3300 to 3400 region, because there's no OHs or NHs in this molecule. So this is a very useful thing, infrared spectra. It'll tell us, infrared spectroscopy will tell us about the bonding involved. Carboxylic acids combine two parts. They combine OHs and CO double bond regions. So notice here, this is acetic acid. We see a very strong signal here at 1700. That's for this CO double bond. And we see this big rounded region. Now, the OH in a carboxylic acid, because it's got a different pKa, turns out to be shifted relative to alcohols. It's broader and it's more around 3000 rather than the alcohols that were a little bit narrower and a little bit to the left. But we see a combination of an OH signal and a CO double bond signal, and that's indicative of a carboxylic acid. Now those are the most obvious things. When I'm looking at infrared, I don't look at much other than those things that I just told you about. I am going to look for the presence or absence of functional groups based on signals in those key regions. So when I look at an IR, I don't spend a lot of time on it. I look at these specific things. By the way, I should note, my presentation of spectroscopy is going to be highly practical. I'm not going to spend so much time on the theory. I'm going to spend most of my time on, I'm going to look at the spectrum and see what I can learn about the molecule. So for instance, I'm going to look at essentially 5 regions in the infrared. I'm going to look in this region, around 3300, 3400. There I'm looking at OHs and NHs. I'm going to look at the region just to the left of 3000, say 3000 to 3050 or maybe even 3100. That's where alkene or sp2 CHs come. Just to the right of 3000, that's where sp3 CHs come. Around 2200 is where I would see a signal if I had a triple bond, and around 1700 is where I would see a CO double bond. So, for instance, in this picture, I see the infrared spectrum of, what is this? 5-hydroxy 2-pentanone. And you'll notice in this molecule, I have an OH, and I see a signal here. I don't have any sp2CHs, and I don't see any signal here. I do have sp3CHs on these positions, and I see signals here. I do not have any triple bond. I don't see a signal here, but I do have a CO double bond, and I see a signal here. So I look for, notice both the presence, so I see a signal here, here, and here. So that tells me that I've got an OH, an sp3CH, and a CO double bond. But also the absence of signals. I don't have an alkene CH, I don't have a triple bond. By the way, this picture here is to remind me of the story of Sherlock Holmes, who told Watson that the key clue in solving the murder was the dog that barked at midnight. And Watson said, "But Holmes, the dog did not bark at midnight." And Sherlock Holmes says, "Exactly. The key to him was the fact that the dog didn't bark, and therefore the dog knew the murderer." And that helped him determine who the murderer was. If it had been a stranger, he said the dog would have barked, and he would have had a signal. Since it was not a stranger, the dog didn't bark, or he saw the absence of a signal. The absence of a signal also tells us information about the molecule. I know that this molecule can't have a triple bond because I don't see any signal around 2200. Now we should be careful. IR only tells us so much. It tells us the types of bonding, but it doesn't tell us the structure overall. For instance, which of these molecules is 2-pentanone? Now if you think about it, 2-pentanone, it doesn't have an OH. None of these 4 have an OH. Ignore this little blip, for instance. 2-pentanone does not have sp2CHs, and in none of these spectra do we see an sp2CH signal, because that would come just to the left of 3000, right in this region. Pentanone has sp3CHs, and all 4 of these have signal just to the right of 3000. None of these spectra have a triple bond signal, and that's consistent with 2-pentanone, and they all have a ketone. We see that signal for a CO double bond. But only one of them is for 2-pentanone, the upper left-hand corner spectrum. These others are for other ketones, because you know what? Any saturated, that is, with no double alkenes or alkynes, ketone, they're all going to have the same type of signal. And notice there are similarities between each of these spectra, right? There's a signal here and a signal here. They don't look exactly the same, but they're in pretty much the same area. But notice there's also differences. Compare this region here to this region over here. These regions are called the fingerprint region. like 1500 to about 500. Now, a fingerprint is characteristic, right? If I am at a crime scene and I find a fingerprint, that fingerprint belongs to a specific person. But I can't look at the fingerprint and say, oh, from the fingerprint, that person is so and such tall and has such and such eye color or anything like that. But what I can do is if I come up with a suspect through another means, I could compare my suspect to my fingerprint and decide if they're the same or if they're different. The same is true about this region of the infrared. It shows if two compounds are the same or different. This region is different from this region, and so I know that these two are not the same compound. If I had a standard to compare, for instance, if I had authentic samples of 2-pentanone, cyclopentanone, 2-heptanone, and 2-butanone, if I had bottles of these on the shelf, and I had an unknown, I could say which one does it match by comparing them. Or if I had a big book, and I'm going to show you in lab 3 big books that are very, very heavy and large, that are just full of spectra, I could compare something and decide which one it is closest to. And that could be very useful. If I had a computerized database, I could compare my spectrum to a computerized database and much more quickly figure out which thing it matches. By the way, this is done a lot in, for instance, like a forensic chemistry lab. Think about watching CSI and they find some substance. They take a spectrum and then they compare it to a database. And in that database they have like all the known drugs and poisons. And they say, oh, this is, cocaine or opium or cyanide or something, because they've matched the spectrum. So the fingerprint region doesn't tell you the structure. I can't look at the fingerprint region and say, oh, I have a 5-membered ring because of this squiggle and this squiggle and this squiggle. Or I've got, 7 carbons in a row because of this. But what I can do is I can use this to compare things. All right, let's do a little exercise here. Excuse me. Here I've got 4 spectra and 4 molecules. Each of these molecules corresponds to one of the spectra. Which one's which? Well, let's look at these. Remember I said I'm going to look at 5 regions. In fact, this first region is characteristic of OHs and NHs. In this spectrum and this spectrum, I see a very broad signal. In that broad rounded signal in that region, that's characteristic of OHs. Do any of my molecules have alcohols? Well, yeah, this one and this one. So this one and this one correspond to these two. Not sure which one is which yet. I'll get to that. The other 2 don't have OHs. There's no big signal here or here. So they must correspond to this one or this one. Okay, let's go to this next region, just to the left of 3000. I see a signal here, but not here, here, or here. I know that that region corresponds to sp2CHs. Hey, this one has sp2CHs and an OH, sp2CH and an OH. So it seems like this one corresponds to this. None of these other molecules have sp2CHs, and so therefore they must be the other 3. All right. This next region is where triple bonds, this region just to the right of 3000 is where things with sp3CHs come. Now, this isn't very helpful to us in this instance because all 4 of these have signal and all 4 of these have sp3CHs. So that doesn't differentiate. This region tells us about triple bonds. If I had a triple bond, I'd see a sharp signal in this region, but I don't. None of these have triple bonds. But this region that I've highlighted in purple, that corresponds to CO double bonds. I see a very strong signal here, and not in the others. By the way, that's not a very strong signal. That turns out to be a CC double bond in this instance. But this one's really obvious. If I see a really obvious signal there, I'm going to say CO double bond. All right, let's put this together. This first one we agreed had an OH and an sp2CH, so that's got to be this. This bottom one's got an OH, but no alkene CHs, so that's got to be this. So I've accounted for this one and this one. This second molecule has a CO double bond, and the third molecule does not. And so my last two possibilities were 2-butanone and 1-methoxypropane. And it turns out that this one with the CO double bond has to be this. And by the process of elimination, this spectrum corresponds to this molecule. Or in other words, this is the attribution. Now, infrared tells us a little. It tells us a little bit about the type of bonding in a molecule, but it only gets us so far. To get any further, we're going to need other techniques, like this is IR, like UV-Vis, mass spec, and the most important technique will be NMR spectroscopy. All right, with that, we'll say goodbye. Thank you for listening. And when we come back, we will talk about nuclear magnetic resonance, also known as NMR.